Thanks for all the questions. By the way, I'll emphasize something that I kind of slightly mumbled as I was looking at my earlier slide, was that when I was talking about payoffs as growth and comparing a payoff of 2 to a payoff of half-half across 1 and 3, if you were talking about a big population who were going 1 and 3 half-half, then every generation you can average and it'll be like everybody having 2 offspring. It'll be exactly the same as everybody having 2 offspring. However, if your uncertainty, the uncertainty of the randomization affects everybody equally, for instance, there's either a famine or there's not, and so when there's the bad times, everyone has 1 child, and when there's the good times, everyone has 3. Well, in that case, the average growth of the population is going to be √3 per period rather than doubling. So, yeah, that's just clarifying. And I think we're ready to start now. Yeah, perfect. Okay, welcome back. These slides may have more typos than the previous ones due to the constraints of life. And yeah, anyway, solutions from dynamics, equilibria as conventions. And let's see, you seem like a smart bunch, so maybe I can start going faster. Faster until everyone goes to sleep, or faster until we finish. Right, so this is what we saw last lecture. Again, I'm going to assume you still have all notation in your head. And we saw a lot of solutions that it's possible to think about, to talk about, to justify to a greater or lesser extent. Now, it's possible to think of solutions as the outcomes of a dynamic process. So you find yourself somewhere and you say, how did I get here? Right? And there's usually an answer. Probably involves some bad decisions you made in your life, but there's usually an answer. So you can think of solutions as the output from processes of strategy updating, and so you can think about what solutions might emerge or be relevant to different types of behavior. In general, we're going to think of today we'll think of some Markov processes, say Markov chains, because I'm going to have finite time, finite state space, on the space S of strategy profiles. So we're going to be at a strategy profile, and then the next period, we might move to another strategy profile. Somebody's going to change their strategy somehow. Assume time is discrete. And P, the Markov kernel, tells us the probability of moving from one strategy profile to another. So when we write P S S dash, it's the probability, given that you're at S, of next period being at S dash. Yeah. Given that at time t you're here, time t plus 1, you are here with probability P S S dash. And we want to construct, how might people change behavior? Thinking of yourselves in some strategy profile, you think of how might you change behavior? You might look at what other people are doing. You might say, well, last period, you got a very good payoff, so I should definitely copy you. So I'll try that. I might say, oh, there's a really popular strategy. Perhaps I should copy the most popular strategy. You might, and most of today we'll be looking at this, you might look around, see what people are doing, and you might best respond. If I have a chance to update my strategy, I might choose a best response. you can also have updating rules that probably won't get to today, but there could be a group of us who might meet and agree to update our strategies together as part of a coalition. So you can think of different ways in which this could happen. Here we're going to start off looking at processes that are built from individual behavior. So an individual being, say, any one of us or any one of the agents in our setup. And so we're going to want a behavior to be able to define a behavioral rule for an individual player. Right? So not just the Markov process for the system as a whole, but for each individual. So it was just P for the system as a whole. For player I, we're just going to use PI to mean the behavioral rule for player I. And this is also going to be a Markov kernel, Markov process on the strategy space, under the restriction that you can't change other people's strategies. You can only change your own. So if S dash involves changing somebody else's strategy, when you're going from S to S dash, it involves changing more than just player I's strategy, then it's got zero probability of happening. Zero probability of me waking up thinking, how should I change my life, and instead changing your life, right? Just got to change my own life. Oh, sorry about that. So that's the behavioral rule. Can't change the strategy of any player other than yourself. And let's construct a process, an overall process, by selecting an updating player according to a probability measure new with full support on the set of players. And then we're going to update according to this player's behavioral rule. Now, okay, first to reiterate what I said, you're the players. I'm just going to randomly pick one person, and then you're going to update according to your behavioral rule. And then we go to the next period. I randomly pick another person, and we do it again. Right? Periods could be short, they could be long, but this is what we're going to do. You can do lots of players doing it at once, but for now, let's keep it simple. Let's just have one person at a time updating their strategy. That makes it kind of, we can just write the combined process like this. It's the probability of selecting player I, the probability that player I moves you from S to S dash. So far, so simple. We're putting a P, this process P, on the game. So it's going to be this process on the set of strategy profiles. Now, let's start off with best response-led behavioral rules. So recall that this is a best response if it's the best. If it's a best response to S minus I, if it's the best that I could do given S minus I. And we could have a behavioral rule that follows best response by saying player I the probability of moving to a strategy Si dash, remember he's not changing anything that other people are doing, probability of moving to Si dash is positive if and only if Si dash is a best response to what the other players are currently doing. So player is chosen, the player best response. In this case, well, imagine you're currently at HD. Earthquake? Do you get earthquakes here? Okay. You do? Not much, okay. Maybe it's probably a truck going by. In Japan, everything's made of wood, so it's kind of indistinguishable. It's like, oh, is it a garbage truck or an earthquake? Okay, well, never mind. So say you're at HD, and oh, I've got pi there. It should be new. It's from an old slide, old image. So you select player 1 to update. Now, given you're currently at HD, the best response for player 1 to what everybody else is doing, to D, is to play D. So switches to D. Now, if every player follows this kind of best response rule, and remember, I'm picking one of you to update every period, then the absorbing states are going to be where every player is playing a unique best response, right? Because imagine everybody's not playing a unique best response. So if you're not playing a best response, I select you to update, you switch. So we weren't at an absorbing state to begin with. Also, if the best response isn't unique, well, the way we specified it here was we gave it a positive probability. We gave a positive probability to every best response, right? So if your best response isn't unique, you would still have some possibility of sliding away from where you are at the moment. Even if you were currently playing a best response, if you had another one, you might just play that instead. You know, two things, they're both good, you might change. So an absorbing state is where every player is playing a unique best response. So those are the strict Nash equilibria of the game, right? If we have a state, we have a strategy profile where everybody's playing a unique best response, this is the definition of a strict Nash equilibrium. So somewhere like, well, like DD or HH there. Don't know why I'm using D in this image, but I am. It looks, it's basically, it's the stag hunt we had before, but with some letters that have magically changed. Note, convergence is not guaranteed to a strict Nash equilibrium. Dear. Oh, of course, yes, it does, it does. So I was halfway on the step. I have a friend and co-author in Zurich, and he says to me, he said, what is this stag and hare? How can anyone who's not a native English speaker understand what a stag and a hare are? He said, you should have deer and a rabbit. And so, yes, this is obviously a kind of halfway house where I was using H to represent something else. No, sorry, I was using maybe R to represent something else, so couldn't actually include a rabbit in my model. So, yes. Yeah, R is, well, yeah, R, Rowena. She was probably being used as a tag there. Thank you for solving the mystery. This is much appreciated. And anyway, so we don't here, you can kind of see in an example like this, we've got two strict Nash equilibria, DD and HH. And if you are every period selecting one of the players to play a best response, you will converge, immediately to one of these strict Nash equilibria, right? And if you imagine a game, if there's a path of best responses from anywhere from any strategy profile you might find yourself at, if there's a path of best responses to a strict Nash equilibrium, eventually you'll take one of those paths. But there might not always be such a path. And the obvious time where there's not such a path is where there's no strict Nash equilibrium. If there's no strict Nash equilibrium, you could follow this best response rule and cycle. Right? See, there's no strict Nash equilibrium. The process is never going to stop. The other case is when there is a strict Nash equilibrium. So here AA is strict Nash, but you might find yourself in a cycle going from BB to, so the best response for Rowena is C. Best response then of Colin is C. And you end up doing this. It's a cycling dynamic, which is sometimes called matching pennies, right? Although I eliminated the name after one of my students a few years ago did a presentation, spelled pennies wrong, and I had to keep a straight face throughout his entire presentation, which was quite difficult. Anyway, in this case, under this simple best responding setup, you'd get stuck. So you might get stuck circling around here. That would be a kind of absorbing cycle. There's an absorbing strict Nash equilibrium. Anyway, sometimes you will converge. So let's think about cases where you do converge to a strict Nash equilibrium. Now, this kind of model has been postulated, first David Lewis in 1969, as a model, a way to model conventional behavior, a way to think of conventional behavior. And by conventional behavior, he thinks of a regularity amongst members of a population in a given situation, such that everybody confirms the regularity all of the time, right? So there are certain regularities we're conforming to. Everybody's wearing clothes. Everybody expects one. I think it applies to the same example. Everyone expects everybody to conform to the regularity. And given that everybody's conforming, and everybody expects, so given that everybody's conforming, everybody wants to conform. And the examples are, the classic example given is always which side of the road to drive on, right? If everybody's driving on the left, and everybody expects everybody to drive on the left, then what would you like to do? Well, then people would like to drive on the left. They'd like to do the same thing. Is it good manners to hold a door open for someone else? So there are regularities about that. Many years ago, I held a door open for a Chinese friend of mine, and she said, "No, you shouldn't do that. You should go through first, so that if there's someone who's going to attack us, you can deal with them first." So there's obviously multiple equilibria in those kind of situations. Appropriate clothes to wear to the office. Circumcision is just one I added after I had some dealings with some papers recently on female circumcision in Africa and data sets from that. And they also, it fits the definition we have above, right? It's very much a matter of conforming and playing a coordination game with one's neighbors. So, you have these, and you can see that these are, this is basically a coordination game. It's basically our, well, it's become a deer hunt now. It's basically our deer hunt, or another coordination game where if everyone's playing deer and you expect everybody who you might associate with, let's say you're matched randomly to other people to play this 2x2 game. So every period I bump into someone and we play the deer hunt. If I expect them to play D, then I should be playing D. But you could say the same thing for H. Right? So you could think of a population of us where we're all randomly matched to play this game when we bump into one another. It could settle on a convention where we're all playing D and expecting other players to play D, or you could settle on the opposite convention where we're playing H. So there's this aspect of coordination underlying conventional behavior. It can still be asymmetric, right? It can still be, you can still coordinate on an asymmetric convention. The classic example Lewis gives is, because he's using a world of landline telephones, is that if the phone cuts out, if the call cuts out, who calls back? You know, is it the person who made the first? Because if you both try to call back, it doesn't go through because you picked up your phones. So, most of you aren't old enough to remember this, but there's possibly, I don't know. We had a phone upstairs which had the little rotary dialer, which is tremendous fun. Anyway, so there, perhaps the rule would be something like the person who called was the person who also calls back, or perhaps it could be the other person. Similarly with the door example was sex-specific, right? So you hold open a door for a woman, right? Even if it's the correct thing to do in that case, it might not be the correct thing to do if you're with, I don't know. Well, if you're the woman, I don't know. So it could be an asymmetric convention. So given the possibility of multiple conventions, multiple stable equilibria, how can we decide which, if any, will occur in the long run? So that's a question that people have asked. In game theory, people think of that. Sometimes if you've got a solution concept that you like, and you want to have that solution concept, but perhaps it doesn't quite give you it's not as fine as you'd like it to be. You'd like to select something within that. A bit like the examples we said about perhaps choosing a Rawlsian solution within a set of Nash solutions earlier. So you may want to select a solution within a solution. Something people call refinement. Actually refining your solution, getting a smaller set of things to consider. In this case, you can see it can be a bit like asking which conventions are most stable. And to get that, because under the previous setup, which you get to a Nash equilibrium, you stay there, it's an absorbing state, but you can perturb the process, and simultaneously, it's going to give us some extra power in looking for solutions, at the same time as a little bit more realism with aspects of the model. And so if you were to go back to the philosophy book of Lewis, 1969, about conventions, I think it's chapter 2, it's called something like Conventions Refined, and it's probably the least interesting chapter of the book, because it's basically just adding most to everything in his definition. But it's a philosophy book, so it's obviously quite longer. And there's good things in there. That's all. It's an excellent book. But a lot of that chapter is adding most. So making it a little bit fuzzy around the edges, making the definition a little bit fuzzy. So rather than saying all people conform to the regularity all of the time, you could say most people conform most of the time. So there are perhaps some nonconformists who just like to drive on the wrong side of the road to scare people. And there are perhaps good reasons you might not always drive on the correct side of the road. Perhaps it's full of holes, right? The joke when I was in Armenia years ago, my father lives in Armenia, was that you take a car somewhere and you'd ask the driver why he was driving on the illegal side of the road, and he'd say because of all the holes. But then you'd be driving back and he'd be doing the same thing. But anyway, this adds some most. You know, what you mostly expect most of the time. I expect you to do this, but maybe I only expect you to do it with a 99%, 95% probability. So you're adding a little bit of fuzziness. So we'd like to perturb aspects of the process of decision-making so that one or more of actions, expectations, or preferences are noisy, meaning random. So a really simple way to do this would be just to add a mistake probability. So let's consider a behavioral rule whereby, so we're just indexing it by this epsilon, see why in a second. With probability 1 minus epsilon, you choose a best response as before. You follow that normal best response update. But with probability epsilon, you randomize uniformly across your set of strategies. Fine, that's just you making a mistake. Something went wrong, you randomize uniformly. This is an example of a perturbed process. You can think of it as being a perturbation of best response, right? If epsilon's very small, you let epsilon go to 0, you go towards best response. And this is a bit of noise, it's a perturbation of that. And in this case, it's uniform. It doesn't need to be uniform. We can add structure to that kind of mistake process. Not going to be doing that right now, but you can imagine situations where you make mistakes that are somewhat hopeful. So imagining you're at some kind of equilibrium of a bargaining setup, but your mistakes always involve asking for more, right? You can have some level of intentionality, you know, even if it's not wholly rational, because you're going to miscoordinate, but you can have some level of intentionality to your irrational behavior. But in this case, just imagine randomized uniformly. This gives a family of processes for player I, indexed by the frequency of perturbations. And if we were to take epsilon to 0, you get this convergence to pi0, and pi0 is actually our previous rule before we added our epsilon. If there are multiple best responses, there could be multiple rules that satisfy our previous rule, but let's assume we come up with a family of these that converges nicely. We're not mickeying around by changing, if we have multiple best responses, changing the weighting between them as we converge to this, a best response rule. And our relationship between perturbed process and perturbed behavioral rules is exactly the same as before. We're just going to choose a player, the player will update, and their update according to their behavioral rule, which is now a little bit noisy. So consider a 3-player symmetric game. This is an example I came up with yesterday. So if you're looking for a place where there might be a mistake, where you're looking for it, this is a good place. So a 3-player symmetric game, and they've got 2 strategies, A and B. Each player has. And B gives you a payoff of 3, always. And A is somewhat more risky. A gives you a payoff of 2 times the number of players who are playing A. So if you think about that, that would mean if of the 3 players, I'm the only one who plays A, I get a payoff of 2. If at least one other person is playing A, I'd get a payoff of 4, or if they both were, 6. So looking at what other players are doing, playing A is a best response if and only if at least one of the other players is playing A. Right? If at least one of the other 2 is playing A, I want to play A. You can think of this as some setting where A is more fun than B, but you don't want to do A on your own. Yeah? There are situations like that. Sometimes conversation doesn't resolve them, right? But particularly, it could be cultural. You know, when you speak to your friend, you're like, yeah, what would you like to do? And they're trying to guess what you want to do, right? And you can end up with some miscoordination. So why did you say you should do it? Oh, I thought you wanted to do it. So anyway, this situation, A is better, but you want to do it with somebody else. Now, best responses are always unique. I've chosen the numbers for that. And A is the best response for player I if and only if some other player plays A. Fine. So under just normal best response without perturbations, what's going to happen? You've got three players, you're picking one, looking at what the other two are doing, then they're choosing A or B. Eventually, you can prove it, you'll reach an absorbing state AAA or BBB in finite time with probability 1. So you're going to reach one of those strict Nash equilibria of this three-player coordination game. Okay, so what does adding the perturbation give us? What does adding the noise give us? Because we've got these two setups, these two kind of conventional ways to behave, playing A or playing B. You can say which one is more robust in some sense. So let's have a look at it with our uniform perturbations. Well, there are no absorbing states because when you update, there's always some small chance that you just randomize, right? So if you let enough time elapse, you're always going to see everything. Right? It's just a toy model, don't worry. There's going to be a unique stationary distribution as well, this Markov chain. So this tells you it's also going ergodic, so it tells you in the long run, it tells you how much time the process spends at each strategy profile. So this is a probability measure over strategy profiles. And for small epsilon, so if we've got non-best responses being quite rare, the process is usually going to be one of the strict Nash equilibria, because you imagine non-best response being very rare, usually you've converged to one of the strict Nash equilibria, you stay there, you stay there, you stay there, until some errors happen, until some perturbations shock the system, and you get some non-best responses, which might take you somewhere else or might not. Okay. Let's stop here for a second, just think through it. Well, okay, you'll spend most of your time at AAA or BBB. Now, if we're at BBB, what could happen? Imagine one of the players, you're just staying at BBB, and then imagine one of the players accidentally plays A. It's a perturbation. It occurs with probability epsilon. And then imagine the next player to update is one of the other players. So now the other player, if he sees an A, his best response is to switch to A, and then wait a little while. Well, now everybody's best response is A, so you could converge to A. Of course, a mistake in playing A doesn't guarantee that you'll go there, because if you're the next person to, if I make a mistake, and then I'm also the next person to update, I might say, oh, okay, they're all playing B, I'll switch, I'll play B, I should play B. So, but it would take one perturbation to move you away from BBB to AAA. If you're at AAA, and you have a perturbation and someone plays B, then now everyone's best response is still A, right? So, because from everybody's point of view, there's always at least one other player playing A. So you'd need more. You'd kind of need to have one player accidentally play B, and then another player accidentally play B before that one switches back, right? So it's going to have to be fast, because before this guy switches back to A, which he will when he's got another chance to best respond, you'd need another player to make an error, switch to B, and then if that person best responded, they would also switch to B. So to move from AAA to BBB, you'd need kind of two pieces of noise, and they'd need to occur quite close to each other in time, right? because you'd usually almost always, if they're very rare, because they have to occur before the one who's made a mistake gets a chance to switch back. So, transitions from AAA to BBB require two non-best responses close together in time. This is a probability of order epsilon squared. So events of order epsilon, two of them, epsilon squared. A transition in the other direction, one non-best response, probability of order. Here, typo. So yeah, this is just of order epsilon here, right? Everybody noting the typo? It's very good. And so because of the thing I haven't written, the process spends more time at AAA than at BBB. I mean, simply because spending almost all its time at one of them, and you've got your transitions from AAA to BBB are quite difficult, occurring these events of that order of probability, and these ones are order epsilon. Could probably do without the big O notation, but so for small epsilon, it's much easier to move towards A than towards B, right? You can see how much easier it's well, you can measure that by epsilon. And what is, if you've got how rare is an epsilon squared event relative to an epsilon event? Well, the answer is epsilon, right? And so if epsilon goes to 0, you become infinitesimally likely to move from AAA to BBB as you are to move in the other direction, right? So it's still rare, but there's one thing is rare, one transition is rare, and one transition is, I can't say twice as rare, really, can I? Squared is rare, a lot more rare. So the process, as you let epsilon, where did I put the control? As you let epsilon go smaller, the probability, the time the process spends at AAA is going to get bigger and bigger and bigger and bigger as a share of all the time. It's like, because the transitions away are going to be, I mean, and I'm ignoring all the other strategy profiles from which it's easy to converge to a Nash equilibrium. Going away and spending some time away at BBB is all very well, but you don't spend as much time away as you spend waiting for the next trip. So the amount of time you spend at AAA goes to 1 as epsilon goes to 0. And so the limit of these processes selects a strict subset of the set of strict Nash equilibria, right? So we had 2 strict Nash equilibria, AAA and BBB, and they are under just best response. Either of them is an absorbing state. But if instead we consider this perturbed setup, and then we take a limit, so we say rather than consider the unperturbed setup, we consider the limits of just a tiny amount of perturbations, well, then all of the weight goes on AAA. We have selection. Okay, we're about to get a little bit more. So far, so simple, right? I hope so.
One quick clarification.
Oh, no.
So in the Markov process which you're talking about,
Yes.
that every step only a single player update strategy?
Yes.
That's what
Yes, yeah. It's, it doesn't do any heavy lifting for us. It just keeps it simple. Yeah, I mean, it's it's fine for more than one player to update, but it can change things, particularly in small examples like the one we just did. But from a didactic point of view, I find it nicer to do one at a time. Yes. So, okay, so simple so far, which is, as I thought, I had the worry, perhaps it's too easy for you guys. Don't know. It's always the curse of starting off, right? Everyone else has already got to judge the audience. Let's get a bit more aggressive in some ways. And there's going to be a slight notation change here as well that says, due to not having enough time. Anyway, we're going to look at a bigger set of coordination games. Let's look at, and I'll tell you the notation change. Up to now, we've used small pi as our general payoff function. Here, I'm just going to use big pi as the payoff function from playing against everybody. And I'm using small pi as the payoffs in this 2x2 game. And the big pi is going to come from combining lots of small pies. Okay, so we're going to have a set of players as before, that's fine, and they've got strategies. A and B are the only two strategies players have. They are essentially, I'm running out of space, so I shall delete something. Playing on a network. So, let's imagine, I guess I'll make them orange. Got a lot of players. And there are connections between them. The players have strategies A and B. Connections between players. And these are going to be weights. They're going to be non-negative weights. So player I cares, so let's say this is player I. This is player J. The weight that player I puts on J is this, Wij. The weight that player I puts on J. So it's the amount that player I cares about what player J is going to do. If that's K, then yeah, you'd also have Wik. You have, well, this is going to be bidirectional, right? It's a directed, weighted graph. So I guess that's why I haven't drawn it, because it's annoying. But got this directed, weighted graph telling you how much everybody cares about other people. It's obviously realistic. You care about people differently. Now, you play a strategy, and your payoff, given what everybody plays, is a sum over all the other players of playing this 2x2 game against all the other players, with your payoff from playing each of them depending on your Wij. So my payoff from playing you is Wij times by, well, what I would get from playing that game in a 2x2 game. So yeah, this is the influence of player J on player I. If I said how much they care about it, it's really, they needn't even be thinking necessarily, right? So it's the influence on the payoffs of player I. And this is a coordination game with a risk-dominant strategy A. So assuming it's a coordination game, so that means this number is bigger than this number, and this number is, well, at least as big as this number. It's bigger than this number, let's say strict. This number is bigger than this number, and A is going to be risk dominant. So I've written it in terms of differences here. Rearranging, you can see it's the same as saying this plus this is more than this plus this. The way I've written it is the same. This minus this is more than this minus this. So let's, how are we doing for time? Great. Okay. Let's go to a larger class of behavioral rules, right? Because so far we were just looking at the perturbations that were the uniform. Very simple, very basic. So let's write the payoff loss when changing strategy from S. So this is the payoff loss to player I from switching from SI to SI dash. So remember, there's only two strategies. Yeah? So the payoff loss from changing your strategy when the whole population's at strategy profile S is well defined, because strategy profile S includes your own strategy. And if you change it, there's only one thing you could be changing it to, because you only have two options. So this is how much you'd lose changing your strategy when the current profile is S. If this is negative, it's a gain. Yeah? If you have a negative loss, it's a gain. Right. But if this is positive, it's a loss. And now we're going to have the probability of player I changing strategy have the order of magnitude epsilon to the Fi of delta I. It's basically going to be, F is going to be a non-decreasing function of your payoff loss, and the probability of changing strategy is going to, well, remember that this is epsilon to the power of something, so epsilon's small, so if it's to the power of a bigger number, it becomes smaller, right? Yeah, epsilon squared is less than epsilon. Epsilon to the million is less than epsilon to the 9. So this means that where payoff losses are greater, you're going to have a lower chance, possibly weakly lower, I'll find out, of changing your strategy. So if changing your strategy is worse for you, you're going to be less likely to do it. And, oh, this is to R plus, by the way, so we can't have negative F's up there. It's epsilon to the power of a 0 or a positive number. That is, probability of changing strategy increases in payoff gain from doing so, or decreases in the payoff loss from doing so, possibly weakly. And this includes rules such as best response with uniform mistakes. That's the one we just looked at, where you had this f function being 0 if x was less than or equal to 0. So if it was a gain, it set the f function equal to 0. Therefore, it was epsilon to the 0, which is 1. It was an event of order 1. And if x was positive, if there was an actual loss, it set it equal to 1. It's just, that was epsilon to the 1, if you were making a loss. But also, I'll leave this with as an exercise to show that this is equivalent to perturbed logic choice. We have f of f is 0 if it's a gain, so that's like before. So it's saying if you improve your payoff, it's something that occurs with an order of magnitude of 1, right? It's not noise. But if you make a loss, actually the probability of making a loss goes down, the bigger the loss is. And this is because logit choice, which is, well, effectively, let's parameterize logit choice. Your payoff from playing something, I guess, let's just call it A, given what other players are doing, is this. You have this specification for logit choice. This would be the probability of choosing A under logit choice, which would be like an exponent of the exponential of the payoff from A. And this is over the one for A and the one for B. So, right, you add the probabilities. You're either going to choose A or B. And then there's this noise parameter here that if you let this go to, I forget the name of this letter. What's the name of this letter? Eta. Eta. Okay, so if you let eta go to 0, then this becomes very powerful, right? And you end up choosing A with probability close to 1 if it has a higher payoff than B, given what other players are doing. And if eta is very it's big, then it's not very powerful. You head towards just random choice. And you can, if you transform this kind of that, then you can turn it into this setup. It's effectively this setup. Anyway, the important thing is that your probability of choosing something decreases in the loss. So, because we used epsilon here, like usually when you, it's just one choice of function, but it's a very popular choice of function, like logit choices, yeah. And then, yeah, using a parameter like that is kind of common, although sometimes you'll see beta written there instead of 1 over eta. Yes. Anyway, it's very popular, and so, yes.
So the question was more this assumption that your probability is proportional to epsilon power fi.
Yes,
that's essential for the
That's
rest.
that's the cheating. So the grain of BS or whatever, I don't know. I'm exaggerating. The fact that it's to a power, right, of this epsilon gives you selective power as epsilon goes to 0, basically, because it means that if one of these f's is bigger than another, it becomes, and then it means when you do it to the epsilon, the difference between them becomes infinite, right? It becomes infinitesimal relative to the other if the f is bigger than the other. So, yeah, it's important. Although, conceptually, you can, of course, define a class of dynamics that doesn't rely on epsilons to have there. And then you can have more fine-grained results within that. But they will be more sensitive to aspects of your model. So that's, yeah. This is one way that you add perturbations, you make perturbations disappear, you get some selection. And of course, if you have the power, you can calculate, you can choose a dynamic you want, you can keep a non-vanishing amount of noise, and you can work out the invariant distributions, you can work out the trajectory probabilities of your dynamics itself, right? That's all doable and all very reasonable if you're actually modeling a specific situation. So, theorem. If every player follows a payoff difference-based rule and A is risk dominant, then A is stochastically stable, by which I mean that the well, everybody playing A, sorry, I guess I'll use it for me. Everybody playing A. This goes to 1 as epsilon goes to 0. So risk dominance is winning for this type of behavioral rule, for payoff difference-based rules. And that applies even if players have different payoff difference-based rules. This is for 2 plus 2. In general, it's possible to state this result, but what you need to do then is what you're effectively doing is you're bundling strategies into strategy A and everything else. And then you have to have conditions, a kind of general form of advantage for strategy A. I'll get into it if I have time, possibly not today, but yes, I'll finish this one, hang on. Yes, so you have a more general form that, that then you get this result. So yes, essentially if the dynamic is asymmetric, it's a formal term towards strategy A, then AAA is stochastically stable. If everybody's behavioral rules are asymmetric towards strategy A, then it's stochastically stable. And this is a kind of subset of that result. Please.
So if I draw analogy with something that is statistical physics we do,
Yeah.
allow you to do that.
Yes.
Then the payoff is like energy.
Yes.
And in that case, I have two related questions. In that case, this AAA, and you have another one BBB.
Yes.
So if you have small systems, that is the number n is small, then there are possibilities of transitions after some time of iterating.
Yes.
Going back and forth.
Yes.
Whether that happens here or not, depending on the system size, that's one question. And second question is that do you have, so the state of the system is given by the strategies, n strategies, right?
Yes.
So then the absorbing state that you mentioned, is it just a steady state without return balance? Or is it a steady state with return balance?
So without is
Without.
yes. So there's you do go back and forth between them, but like for any fixed epsilon, you do go back and forth between them, and there is you can define a. I mean, it differs depending on exactly on your f function, but you can define a potential function that works in this setting. So I mean, these coordination games have a exact potential function, so you end up under the best response dynamic going to a Nash equilibrium, but then you can define a different potential function, like stochastic potential, people tend to call it, for the perturbed dynamic. And then you compare those stochastic potentials, and it tells you which is going to win for the low values of epsilon. So that's, no. But yeah, there is, it is basically like an Ising model, and yeah. Yeah, sure.
So what conditions you need on the network? Does the network have to be strongly connected or?
Well, I mean, yeah, I didn't write down any conditions for WI, but basically, you should depend on at least one other player, right? It's very weak. It doesn't have to be strongly connected. You could, of course, but if it's not connected at all, then, well, then it's just two problems. So you prove the theorem for one of them, then you're there, right? Yeah, yeah. But you shouldn't have a player who just has zero payoff, because then, well, it's almost like there's no problem for them. We should just get rid of anyone who has no dependency on anybody else.
My second question is that stochastically stable in the sense, what sense? Almost surely or?
It's in the sense that the limit of the invariant measure, it's probably, can you see this from here? So the invariant measure puts, the probability it puts on all A goes to 1 as epsilon goes to 0. So for any fixed value of epsilon, you have the invariant measure puts some weight on AAA, and this goes to 1 as epsilon goes to 0. In this example, usually, as long as it goes to something greater than 0, people in the economics will call it stochastically stable, because there could be multiple depending on how kind of fine or crude the process that you set up is. Right? So for example, you can get setups where having uniform mistakes isn't enough to distinguish between equilibria. So you'd need something different. So perhaps something that strictly depends on payoffs to be able to distinguish between them. Okay, another question. You can tell I feel I have time. Well, I actually don't, it's not that I have time or don't have time. It's just that I stop at any time. I can go at any time now. So go.
I didn't get really like how the population was being updated. So is it like every individual is synchronously updating, or
No, just pick asynchronous. Pick one every period.
random?
Yeah, pick one at random.
So the theorem holds for this choice of.
So it's, I mean, it also holds if you have like say an independent, asynchronous and independent, it also holds. Sometimes you need to add a little bit of stickiness such that you don't update all the time, right? But generally, you don't even need to add the stickiness when you're dealing with these perturbed setups. When you've got no perturbations, you can end up with the traffic lights, well, the miscoordinating coordination, right? Where you play B and I play A, and I switch to B to coordinate with you at the same time, you switch to A to coordinate with me, and then we keep doing that forever. But these results for stochastic stability hold even in situations like that. So even in situations where, yeah, we might not necessarily have to have a bit of inertia. But from a modeling point of view, it's usually nicer to have some possibility of inertia so that, as well as being realistic, right? some probability of me just not moving right now. Okay, so this is a result that, so what can I say? It applies to all of these payoff difference-based rules. Should I try, I'll try a little bit of time to explain it as trivially as possible, right? The more trivial I can make it sound, the easier it is to understand, maybe. Hopefully I don't go in the wrong direction. So these rules depend on payoff differences, right? So okay, we have this coordination game. And A is risk dominance. This depends on this inequality here, which says that switching from AA to play B, you lose more than if you were at the B equilibrium and you switched to A. So this definition of risk dominance gives you a kind of asymmetry in payoff differences. Yeah. This tells you that this one's bigger than the other. And then the rules, the updating rules that we just considered, use payoff differences to choose strategies, right? So with larger payoff losses, so here's a loss, larger payoff losses being associated with smaller probabilities. So you are less likely, a single jump like this, imagine you had a two-player network, you'd be less likely to jump away, weakly less likely from AA than you would be to jump away from BB. And that's kind of logic. It's really a baked-in asymmetry towards strategy A in the system. Another way to think about that asymmetry is to think, well, just rearranging this, you've got AA plus AB is greater than or equal to BA plus BB. Or the way we mentioned before, that if everybody was playing A with probability half and B with probability half, your best response would be A. So if you can think of the most symmetric situation possible, it would be something like that, where half the population are playing each thing, or everybody is playing each thing with probability half. And in that situation, the forces push you towards A. And again, that generalizes. So you move from payoff differences in the game, they go into a dynamic that depends on payoff differences, and that leads to selection. There were a lot of papers written about this. It took quite a while for people to figure out what was going on. And once you realize it's due to a basic asymmetry in the rules towards A, you can then take any rule that follows this, put them together so that players in a game play different rules, and you're still getting the selection, right? Because you still have the essential asymmetry of the process. Okay, so we've got 16 minutes. I have more after this, by the way. I have like an intermittent stopping, and then I have about 20 more slides, which we can think about. What did I do? Okay, let's do that after. No, I'll go to asymmetry. I think I have some slides on that. Okay, before finishing that, let's go to here. It's talking about the general case that was asked about. So it's going to be something called asymmetry, like towards strategy A. So here, red is kind of like strategy A was before. So think of a player Alice, and Alice is the member of a set of players, and each player has two strategies, red and transparent. Right? It's going to be apparent why I do this. So, transparent is transparent because you can see through it. And strategy profiles S dash and S dash dash are red associated if every player plays red at S dash or S dash dash. So one way of thinking about that is if we take the two profiles with the red and the transparent and we put them on top of each other, everybody becomes red. All the players look red because it's either a red and a red or a red and a transparent, okay, which looks red. So if it's all red, that means S dash and S double dash are red associated. And then we can define what it means for Alice, for her individual behavioral rule, to be asymmetric towards red. And it's asymmetric towards red if, for any red associated S dash and S double dash, her probability of choosing red, given, we've started her out at non-red here, of choosing red, given this profile here, is at least as great, 2 order of magnitude, as her probability of choosing transparent, given this one here. So what's a couple of ways of thinking about this is, well, you've all heard, may have heard the term like, well, let's write this first. Let's write 1, 2, 1, 2. And then I'm not going to do the one that we see there. I'm going to do another one. It's not just a repeat. Let's do this one. And I'll just draw a line to separate them. This one's S dash, and this one's, well, it's new, so I'll call it S hat. Now, you've all heard of like ceteris paribus, like all else being equal. So like a decision made by Alice, if everything else is equal. But here it's kind of the opposite of that. It's all else being, everything being different here. So comparing these two, they're just the opposite of one another, right? Here, red is played here and here, and something else is played here and here. Transparent is shorthand for something that's not red. And here it's the opposite. And so one, you can see these two are red associated, right? If you put them on top of each other, it's all red. Now, and the asymmetry assumption says that Alice is at least as likely to switch to red from here as she is to switch away from red to here, at here. So all else, everything being different, there's this slight asymmetry towards switching to red. Or it could be a big asymmetry, right? But there's an asymmetry towards switching to red for Alice. Then I have the example like we had up here, which is, so that's part of it. That gives a kind of advantage of Alice, of red over anything else. Then in the example I give up here, I also have this being red. So that says, and then the asymmetry condition says, Alice is still more likely to switch to, I should mark Alice somehow, I shouldn't. Alice is still more likely to switch to red here than she is to switch away from red here. Here it's not, I haven't just flipped everything. I've kind of flipped everything and then added some more reds, right? So you can think of this as meaning that having more reds in the system doesn't reverse that asymmetry, right? Because you can have examples that don't satisfy that first one I saw, where this was transparent, but don't satisfy this. You can have examples where players would like to miscoordinate with as much with the population. And in cases like that, you can have examples that don't satisfy this as well. What this is saying essentially is that more red doesn't hurt in terms of having an asymmetry towards red. Anyway, so this is all else being different. There's this asymmetry towards red. And remember, transparent could be any other strategy that's not red. So this is answering the question from earlier. And if there's a process like the ones we've been looking at, where every period some subset of players, I guess that answers your question too, independently update their strategies given the current strategy profile, and that each player updates with positive probability. Shoot before, you have nobody who just stands there and never updates. Then if every player is asymmetric towards red, because here we were just talking about Alice, if every player has a rule that's asymmetric towards red, then everybody playing red is stochastically stable. And the previous result we saw on risk dominance is a special case of this, where the asymmetry towards strategy A, in what we looked at before, came from the fact that you have these payoff differences. The payoff differences were greater when thinking about the risk dominant strategy, and that made you less likely to move away from it when it was a bad idea to move away from it. Yes, where's that coming from? Okay. I mean, in some extent, that's a tautology, I guess, in that if red eventually takes over, does it have a selective advantage? Yes. I mean, by definition, no. I mean, if it doesn't have any advantage, it wouldn't take over. So that's why I'm saying it's tautology, or, I mean, you're trying to think about it in terms of what related to, say, some reproductive process, or, I mean, it has a selective advantage, yes, right, as expressed by asymmetry.
Is this stochastic stable thing evolutionary stable strategy as well?
Not necessarily. So, I mean, what we've been looking at are I don't know. I mean, so far we've looked at, could you construct a situation where it is? Probably yes. You could look for overlaps. So the examples we saw before were very much driven by players following some rule based on best response. So a kind of rationally founded economics-y style rule, because economists love Nash equilibrium, and so you're like, okay, but how do we get subsets of Nash equilibrium? What can we do? But this, yeah, but you could also have other examples where, because here I'm talking about the asymmetric behavioral rule, it doesn't need to be a Nash-based rule. It could be a rule based on something else. It could be a rule based on imitation. That's absolutely, say, imitates the best, or other forms of imitative rule. Or it could be a process that's, well, imitation is close to replicator style dynamics. So it could be something based on that as well. Now, of course, asymmetry is a product of both the process and the underlying game. So it could be that, so for example, in our payoff difference-based rules, they were asymmetric towards A because A was risk dominant, right? If A wasn't risk dominant, then they wouldn't be asymmetric towards A. So it's a product of both of those things. But yeah, I don't know of any relationship between this result and ESS, or if anyone's looked for it. I mean, the kind of general form of this result is relatively new, so yeah, it's a good question. I don't know under what conditions could there be a relationship between those. I don't know. Anyway, as we're rolling into time, oh goodness, I had more on this. Oh yeah, this is saying risk dominant stuff is a corollary of that. And then let's zoom back to a conclusion slide. So what have we seen in this last hour and 25 minutes, 27 seconds? We've described an approach towards equilibria and equilibrium selection that begins with behavior. And if we know behavior, we can find something like an equilibrium. And that's a little bit opposite to a standard approach in economics, which typically specifies an equilibrium and then searches for the equilibrium and says this is what happens. It doesn't talk specifically about the processes that take you there, the underlying behavioral rules that might take you there. You can consider many behavioral rules in setups like this or adjacent. They could be imitative, coalitional, altruistic. You can have K-level thinking as well. So you can expand on basic best response by iterating it, saying, well, if I best responded, but if everybody else also best responded, then, and then you can iterate a few things, and you can have heterogeneous levels of iteration in the population. You can have weird preferences. You can add very, very odd preferences to amuse yourselves in those hours where you just, well, it's not my fault, where you just want to do some maths, but to no particular end. And you can have, maybe we'll have a chance to see these later in the week, dynamics and models that lead to the core and to stable matchings in matching problems and to various bargaining solutions in bargaining problems. And that is perfect timing. So, like, we had 2 minutes, 51 seconds remaining, apparently, but the battery did the job. And also, I don't need those 2 minutes, 51 seconds. Okay, any questions before lunch? So stochastically stable, this is stochastic stability, yeah, in a way. People tend to talk about it in econ. Right. So, yeah, I mean, you can, what you select depends on the rule, basically. So, yeah, but it depends on the perturbation as well. And generally, risk dominance is pretty strong in these, but I mean, yeah, it depends on the rule. I mean, basically, some guys published a paper that said by choosing appropriate error probabilities, error process, you can select any probability distribution. So assuming like best response plus some errors, by choosing appropriate error probabilities, you can choose any distribution over the Nash equilibria, right? So by choosing an appropriate error probabilities. And that was seen as a terrible thing because people wanted an answer. And if you have another thing where you can select anything, that's not an answer. But really a result like that says that if you change the model, you change the outcome. From my perspective, but for people who are seeing it as a kind of selection tool, like we have a lot of Nash equilibrium, we want to select one, and wanted a firm answer as to something that was good to select, that was seen as a bad thing. They wanted it to be almost behavior independent selection, but that's impossible, right? I mean, because what you put in should determine what you get out, and it'd be super weird if it didn't. But because of the way people were thinking about it from a refinement point of view, that was seen as a disappointment at the time. But I think by now more people understand. But yeah, appropriate rules can pay off dominance winning for sure. Okay. Particularly in imitative ones, like imitative, it's all about who do you copy. Do you copy the cooperator who's 2 steps away on a network, who's surrounded by cooperators, or do you copy the cooperator who's playing you, who's a defector, and because you're a defector, they're doing pretty badly, right? So where do you get your opinion about how good it is to cooperate from? Okay, thanks very much.